For centuries, the stars have inspired us. We've gazed up at them from deserts, oceans, and mountaintops, marveling at their permanence, their brilliance, and their mystery. We've mapped them, navigated by them, prayed to them, and studied them. And today, we know something profound. Those stars are not just lights in the sky. They are engines, nuclear furnaces, burning with unimaginable power, sustaining galaxies, fueling planets, and in at least one known case, giving rise to life. But what if we could do more than admire the stars? What if we could harness them? What if we could capture even a fraction of their energy, not just to warm ourselves, but to power a civilization? This is the dream of the Dyson sphere, one of the most ambitious and awe-inspiring ideas in the history of science. A theoretical megastructure so vast, it would make every building, every dam, every spacecraft ever constructed seem like a grain of sand by comparison. And yet, the idea is deceptively simple. A Dyson sphere, in its broadest sense, is a system built to capture the energy of a star. Not metaphorically, literally. It's a way to intercept the sunlight that would otherwise spill into empty space, unused and unnoticed. It is, in essence, a solar panel the size of a solar system. The origin of the idea traces back to the visionary physicist Freeman Dyson, who in 1960 published a paper titled Search for Artificial Stellar Sources of Infrared Radiation. In it, he proposed that any sufficiently advanced civilization would eventually build structures around their home star to meet their energy needs. He wasn't describing a solid shell, as science fiction often imagines. That would be physically impossible, structurally unstable, and gravitationally catastrophic. Instead, he envisioned a Dyson swarm, a cloud of independent satellites or energy collectors orbiting in formation around a star. Each one would harvest sunlight and transmit the energy, perhaps via laser or microwave beam, back to habitats, planets, or energy storage stations. In Dyson's view, this wasn't fantasy. It was the logical next step in the technological evolution of any intelligent species. Just as early humans burned wood, and modern societies burn coal or harness wind, so too might future civilizations tap into the greatest energy source available to them, their star. To understand the scale of the Dyson sphere, we first have to understand the scale of the sun. Every second, our sun emits around 3.8x10 superscript 2 watts of power. That's 384 yottawatts, a number so vast it strains human comprehension. To put it in perspective, all of humanity's current power consumption, every city, every factory, every phone, every rocket, amounts to about 20 terawatts. That's just 0.000000000005% of the sun's total output. In other words, the sun gives off more energy every second than humanity has consumed in its entire history. And we are only catching the tiniest sliver of it, just the sunlight that reaches Earth. Everything else, it's lost, radiated into space, wasted. The Dyson sphere is a way of changing that equation, of expanding the net, of intercepting all that power and using it for something more. But what would we use it for? More than you might think. An energy supply on that scale could end all energy scarcity forever. It would enable post-scarcity economics, where energy is not a constraint on human growth, comfort, or exploration. Poverty, at least in energy terms, would be eliminated. Wars over oil, gas, and grid access would become relics of the past. We could desalinate oceans to end water shortages, power global-scale weather control systems, maintain entire continents of smart infrastructure, AI, and robotics. More ambitiously, we could power interstellar missions, sending probes or even humans to other stars. We could terraform Mars, build colonies in orbit, or construct artificial worlds, massive rotating habitats like O'Neill cylinders. We could simulate entire universes, build brain-computer interfaces, and perhaps even digitize consciousness. These are the kinds of dreams that require not just incremental growth, but orders of magnitude more energy. Energy we can't find on Earth, but that we can harvest from the sun. So how could we begin? A full Dyson swarm would take millions, even billions, of individual units, solar collectors, orbital platforms, energy relays. Constructing them on Earth and launching them into space would be cost-prohibitive and dangerously inefficient. Instead, we need to move industry off-world. That means mining asteroids for raw materials, carbon, silicon, metals, and constructing components in orbit or on the moon, where there's no atmosphere and far less gravity. We'd need robotic assembly lines, operating in vacuum, self-replicating, and self-sustaining. We'd need beamed power technology, microwave or laser systems that can transmit harvested energy safely over millions of kilometers. We'd need AI systems to coordinate orbital logistics, and advanced materials that can survive years of solar radiation without degrading. None of this is beyond the realm of physics. It's just a matter of scale, investment, and time. For now, the idea remains far from reality, but closer than it once was. We're already seeing prototypes of space-based solar power. We've landed spacecraft on asteroids. We've built AI-controlled satellites and developed thin-film solar panels that are ultralight and space-ready. Each of these is a tiny step towards something much bigger. Even modest versions of a Dyson swarm, say, a constellation of energy satellites in orbit, could transform life on Earth. And once we learn to build in space, without relying on Earth's deep gravity well, progress could accelerate rapidly. What starts as a trickle of satellites might become a cloud, and that cloud might one day evolve into a full Dyson swarm, a shimmering envelope around the sun, harvesting its power for generations yet unborn. But the Dyson sphere isn't just a scientific idea. It's a philosophical challenge. It asks us to imagine a future not defined by limitations, but by abundance. Not shaped by scarcity, but by foresight. It asks, will we remain a species bound to one fragile planet? Or will we rise to become something more? Something interplanetary, even interstellar? It also makes us ask another question. If it's such a logical path, why don't we see them? If advanced civilizations build Dyson spheres, shouldn't we spot them in the galaxy? Some scientists are looking for exactly that. Searches for Dyson signatures, stars dimming unnaturally or giving off strange infrared radiation, are already underway. In 2015, astronomers noticed a peculiar star, KIC 846-2852, better known as Tabby's star. It exhibited erratic, unexplained dimming, leading to speculation about possible artificial megastructures. Further study pointed toward natural causes, likely dust clouds or debris. But the idea stuck. Perhaps somewhere, some civilization is building its own Dyson swarm. And perhaps, if we keep looking, we'll find one. If we don't, maybe the galaxy is quieter than we hoped. Or maybe Dyson spheres, once completed, are nearly invisible, silent engines in the dark, built by minds we've never met. In the grand scheme of the cosmos, we are still infants. We've lit sparks, burned fuel, split atoms, but we've barely begun to understand what energy can do, or what we might become when we finally learn to control it. A Dyson sphere is not just about capturing light. It's about becoming light, becoming a species that does not hide in the shadows of its limitations, but steps boldly into the brightness of possibility.